Next up, we have Dr. Tony Sgambellone. He's is a scientific test and analysis techniques expert at the STAT COE Center of Excellence. He's been part of STAT COE since 2020, where he provides support and instruction in efficient and effective test design and analysis across the DoD. Before joining STAT COE, Dr. Sgambellone developed machine learning models in the financial industry and on Agile software development teams in support of customers on Wright Patterson Air Force Base. I learned reading my last bio that I should not try and stumble through other people's degrees because I barely can get through mine. Welcome, Dr. Sgambellone.
Thank you. Yes, it's working. All right. Today, I'm going to talk about a case study. It really illuminates the principle of reducing test to purpose. Okay. Often, when we're designing for tests, it can be really tempting to put all of our focus on how much we can learn about the system, given how much we're able to test. But that's not always what's needed, or what's best for the program. So here we had a program that was doing a flight test for a round, and they found, especially after the flight test was done, they had striations in the protective coating. And you can see the lines on there. It'll be bigger in another picture. Now, these didn't interfere with the flight test that was happening that day, but if they were deep enough, it could significantly impact the performance over a full flight later in the program, which could be a significant risk to the program. So they did a root cause analysis. Okay, were the striations there before? Were they caused by the flight test? They ended up settling on it was probably during storage, where there's the significant weight of the round pressing down on the pads, and the protective coating gives and deforms a little bit. It's known as creep, so it'll be a little thinner under the pad, a little thicker around it. One thing that they thought may have led to this was that the shot was exposed to more than 150 degree temperatures with the effect of the direct sunlight on it a day or two before the test. This is above what's known as the glass transition temperature for this material, which could make it more susceptible to creep or changes in friction. So the test team initially came up with a plan for a triplicated full factorial. Okay. They had 3 factors, 2 to 3 levels for each factor. They were eventually going to increase the number of levels for load, so it was going to be, say, 81 to 110 runs. And this was not ideal for the program. This was not a planned test. It just, surprise. We tested, found something new that needs tested, which is not something you like to have happen, but it's really the reason we test. If nothing unexpected ever came up, then we wouldn't need to test, and doing so would be really boring. Okay. So the program didn't want to divert resources from other parts of the program and schedule to do this, but it's something they were willing to do. And it's something that came up in an earlier session in another room was, well, we have all these options for designing a test. How do you choose which one? If you don't have anyone who's an expert in the field, there's really no easy taxonomy to walk through all the options. So you really do need someone who's familiar with all the methods, who can narrow down, okay, what types of analysis can we do with the data that we would be able to collect? What types of designs will give us the answers we need to answer our question? And then, ideally within those, which ones have the best trade-offs for our purpose? They did have some prior information about the system. They had simulations for how big of a striation would be a problem. And they were pretty confident that any striation that was less than 10 mils, or 10 thousandths of an inch, would not really be a problem for the program. But as soon as it got to 10, anything that large or larger, we would need to detect. They also were able to do some short-term tests in a couple of hours. and a couple of hours of measurements, and they found that the noise in the system seemed to kind of plateau within that time, and it was on the order of a half a mil, okay, or less than a thousandth of an inch. So the signal is what we need to detect. How big of an effect do we need to detect? The noise is if we repeat the same thing, how different are our answers? Well, here we got a signal-to-noise ratio of 20. And anyone who's familiar with that knows that usually makes testing really easy. Okay? The things we need to detect are so much bigger than the noise in the system that could obscure them. So triplicated full factorial is probably not going to be necessary in this case. Okay. Now, they also wanted to test in more ways than one. Okay. They had test case 1, which was to take a column of the material and put it under pressure on its long axis, because this was analogous to a classical material science test to really get an understanding of the material. Then there was also test case 3, which was more how the system was going to be put into use. And test case 2 was a one-off to just confirm some things in between. So we focused on designing for test case 1 and test case 3. For test case 1, we used an eye-optimal design because they were most concerned with being able to predict the overall depth of the striation more so than explaining the differences between factor effects. We gave them a couple candidate designs, which, they don't look too different here, but you can't see which points are replicated there. And we have this handy sheet that we use to help compare, the trade-offs between them. Okay, red isn't necessarily bad, but it's a metric that's not as good as the other ones in that regard. For instance, the one on the left has red sample size. Sample size of 16 is still a lot better than they were expecting to be able to do, but it's the worst of the three, so it's red here. Okay. They ended up choosing the one in the middle, only 13 runs for 3 factors, 3 levels each factor. But our signal-to-noise ratio was so high that our power is rounded to 1 here. We are nearly guaranteed to find any effect that's large enough that we would need to find it. Designed for test case 3, similar principles. Test case 1, one other thing I did not mention is that it's continuously measured over time. So it really only had 2 factors, the pressure and the temperature, because we were able to get not independent, but a whole lot of measurements over time. Test case 3 was more traditional in that all of the measurements were independent. So 3 factors, time was chosen at, 1 level of time per coupon. So the measurements were truly independent for the typical assumptions of the analysis. Again, they went with the smaller one, another 16 runs. Okay. And again, our power is still 1 to the number of decimal places that we could round to in here. So it looks very good. This was nice because we weren't sure that the noise would stay at 0.5 mils, because we're going to be testing a lot longer than the 4 hours of that preliminary test. But even if the noise doubled, we'd still have a 10 to 1 signal-to-noise ratio, and our power, it's not shown here, but it still would have been above 0.95. Now with test case 3, it gets harder to determine exactly what our response variable is going to be, because that pad was uneven. It tends to create 2 striations here, like 2 lines. What is our response for that test coupon? Well, we could go with the maximum depth, and we did look at the maximum depth for each striation, but maybe there's going to be a consistent difference between them. So we actually did a multivariate analysis and considered it to have two response variables, the maximum depth for the left striation and the maximum depth for the right striation. And we also used the percentage of creep rather than the raw depth of the striation. That was deemed to be probably a more consistent measure and would make it easier to compare test case 1 to test case 3. So test case 1 modeling. Okay. Now there are probably existing methods that would account for the correlated measurements, and that when you're measuring almost continuously over time, it's the same coupon. So your measurements aren't independent there. That does violate some of your assumptions for most methods, including regression, which we were using. However, we were on a bit of a tight time schedule, and we also had test case 3 coming later to verify anything that we thought we saw in test case 1. So, and also most of the assumptions for regression are really focused on the validity of a significance test. And even if you violate those assumptions, it can still provide the best linear unbiased estimator. So we're going to see what we could see from the regression, and then we would also take a look at a neural network. Not a terribly complicated one, 2 hidden layers. I don't remember how many nodes were in each layer. I think it was just a multiple of how many factors were available to influence the response. So we started off with the assumption that a transformation for log of time would make the relationship more linear, and it did, but we ended up finding that transforming for log of the creep percentage improved it further. Okay. So you can see the top was just log on the time scale, and down here was log time and creep. It doesn't perfectly match, and you might even consider each one of those discernible lines as a single observation. How well did the regression model predict that line? Yep. We ended up seeing that it looked like the main effects were the most important, followed by a quadratic effect in the pressure, and so forth. It did manage to capture 98% of variation in the system. So it's probably giving us some information to go off of what we should expect to see in test case 3. Then we had the artificial neural network. They are universal estimators in that they can model any shape of relationship. So we would expect this to fit better. And in fact, it did seem to fit the shape better, in all except for this one case in the training data set. But it actually did great in the validation set. However, as powerful as neural networks are, they are not fit for every purpose. This was a designed experiment in which we had 3 specific levels of the factors. Now, this correctly predicted that there would be no creep when you first start at time 0 for 70 psi, and approximately the same for 100 psi. Or, sorry, 50 and 100 were our numbers there. And also, no creep when you first start at time 0 for 200 psi. But because it's able to model any shape, and there was no data to restrict that shape in between those values, we see a spike here at about 190 psi, where, before you even have any time, you have significant creep if it's 190, and that's not realistic. Yeah, so while it was better able to fit the observed and validation data, it would not be a good fit for their purposes of knowing, under what conditions can we expect this to be an acceptable result? And what conditions is our physics-based model also correct? Yeah. How much can we trust that? So it was a fun experiment, but we found that it really wasn't fit to the purpose of this program. Now, we have the test case 3 analysis. We had that multivariate regression, and we found that the maximum depth of each striation was taken, and then we made a model off of each striation. So a model off of the left striations, and then a model off of the right striations. Here, we ended up seeing, this is in order of importance in the final model, which I'll show in a few slides how we got to that. But temperature and pressure were still, as main effects, the most important. But then here we have the quadratic in pressure, and then an interaction before time comes in. This kind of makes sense in that when we were applying regression to test case 1, a lot of the time differences were off of the same coupon. They weren't independent. In here, every different time measurement has the additional variation of a new coupon added to its effect, or our estimation of its effect. So time dropped down. It's still important, but it shows the difference between having, independent observations and the value for that. Okay. So as I said, we made a model off of each set of striations. Turned out that the model for the second striation was a more robust fit, not only on its data, but also for the other striation. So we ended up choosing that as our final model. Now, skip that because that demonstrates just what I said there. Okay. Our final model looked like this. Again, and I guess that wasn't the case with the time. I guess for the model we ended up choosing, time did end up being the third most valuable here. But here is one of my favorite outputs for looking at the shape of a model, the profiler. Most of the time, when I see the quadratic here, me not being an expert on the system that's being tested, but rather just in the methods of test and how to get the answer from the data, I had some doubts about this quadratic here. Okay, maybe it comes up and plateaus. I really didn't see how it could come up and then back down again when you add more pressure and it doesn't creep as fast. Okay. However, the test engineers found that was actually a valid relationship. In this case, if you add enough pressure, it flattens out the pad. Then you don't have two lines of striations anymore, but it's spreading the force over a much larger area, and it really does decrease the rate of creep. So it's really valuable to have people from all the perspectives of the program, like how you do the analysis, the principles of the analysis, the principles of the system, and get everyone in the same room and talking to each other. So yeah, that aided in identifying a new mechanism that affects the creep, so that pressure can be concerning up to a point, but if it's at a low enough temperature that it reaches that flatten out point before it gets too bad, then it can actually withstand a lot more pressure. Okay. Here's some predictions for that model. With the 50 psi and the amount of creep, tends to keep going up over time. These y-axes are not the same. This one's going up to 15, this one's going up to 20. So, it goes more so for the 100 psi. This one only goes up to 14. It comes up and flattens off real quick. So our model was able to detect the effects on creep with a high degree of significance, high degree of certainty, and typically to predict within 0.05 of the transformed units, that log of percent creep. And what this translated to was approximately 1 mil accuracy in the depth of a striation, which was pretty nice for having to predict 10 mil striations. Now that's at low creep values. At high creep values, the error was a bit higher, the residual was a bit higher, but that didn't matter a whole lot to the program because it was already known that the striation would be too deep at those levels. So we were able to satisfy both the goals of general characterization and identifying when there would be creep of practical significance to the program. So the reduced design was built to the program's prior knowledge of the system variability. That's the primary driver for what allowed us to reduce the test and have that be convincing to the decision maker to allow us to save them their time and resources. It was able to meet the program's needs with much lower cost. The program was able to save approximately $200,000 in the test resources, and then also a reduced time to the schedule, which arguably may have been more important to them. Oops. There we go. So, are there any questions?
Possibly a naive question. I'm not an expert in data science or neural networks, but so for your neural network case, it seemed that you had sort of, I guess, unrealistic initial conditions that it was predicting, right? Your issue was that, if I understood correctly, it was that at time zero you were getting non-zero creep values out of the model.
Yes.
Right? And it was kind of just interpolating non-linearly between points, and there was a peak. Have you considered, for cases like this where you know, say, that the initial condition should be zero at time zero, to generate like artificial data points in the training data? So like just for a bunch of conditions at time zero, just put in a zero creep value as a training point, try to avoid that issue?
I think the problem there would be that you would be able to avoid that issue where you'd be able to verify that it's happening. However, you won't be able to interpolate the entire space that way because you don't know what's supposed to be happening over there.
Your regression model is also going to interpolate non-linearly between points, for unseen data points, right?
The regression model is going to interpolate linearly, always. Now, linearly with respect to, say, x squared is not going to look like a straight line on the plot, but it's still extrapolating in a controlled, or interpolating, within a controlled way.
Okay.
So if it's a reasonable fit for the shape of the relationship, you can interpolate.
Understood. Thank you.
You're welcome.
Thank you so much.